Okay. Thank you for reminding me of that. So, as you look through this first section, I hope you felt fairly familiar. So I'm going to speed because I don't think there's much I need to remind you of as far as this goes. If there are questions you have, please answer. Otherwise, we're just going to keep rolling. These lecture slides are up on Schoology, so you're welcome to check them out there. So again, stop me if you need something, right? Why is chemistry so important for anatomy and physiology? Can you all give me a raised hand? Oh, she was up and then she was down. Yes?
For example, a cell breaking part needs intricate molecules to assemble.
Okay, the cells use molecules to assemble. The metabolic processes are basically chemical reactions. I would say that's really what they are, just chemical reactions. Sir?
Body structures and functions of the body
It's all coming from chemical changes. Ansel could summarize this whole entire thing by saying life is chemistry. Right? I mean, that's what it is. It's simply reactions between molecules. Right? So that's why it's important that we as anatomists and physiologists, that we understand this chemistry piece. Okay? How do we start with the smallest pieces of matter, right? Matter is something that takes up space and has mass. That way is actually the wrong word if you want to be true in a physics component. But anything that has mass and takes up space. Because gravity, you need gravity to have weight. You don't have to have gravity in order for there to be mass. But we'll let it go. They're anatomists. They're not physicists. So you folks in physics, you can tolerate that. Mass and takes up space. The smallest little bits of matter are called what? Okay, sure. And if we have, of those atoms, we've got 118 different versions or flavors of those. And we call those what? Elements. Right? We're cool so far? We, in your body, is made up of about 20 different elements. I had somewhere that I forgot to pull up here quick. I know how much you're worth. This is as of last year. I didn't update it for this year with the different prices. But here you go. You are worth about $2,000.
Only?
Oh, I'm sorry. I hate to break the news to you. But if we took you and broke you into all your elements and then sold those elements off, that's about what you're worth. A celebrity would probably be worth less. Yeah.
How?
Okay. This is just simply the basic building blocks of what you are. Okay? Some sugar, some chlorine, some oxygen, some salt. You got plenty of water. Did you see that? 12-gallon jugs of water. And again, we're taking just the average person. There may be some difference between a very large person and a very small person, but right? This is everything. That's everything. This is basically taking your body and breaking it up into the different elements or different compounds. Yeah, no, it's not very much. Not very much. All right, back to our regularly scheduled program. Remember, each atom has a structure, right? At the center of the atom is what? Nucleus. Okay, in that nucleus is made up of two things. Protons and neutrons, right? Protons have what charge? Positive. Neutrons have what charge? They're neutral, no charge. And then around that nucleus rotates electrons, which have what charge? Negative. And the electrons are what really make the difference, right, friends? They're the things that actually do the reacting. Remember that outermost layer? What do we call those? These are all questions that were on your final exam for chemistry, right? The valence electrons on the outside. And it's how those guys interact that's what gives us different reactions. Before we go there, we talk about atomic weight or atomic mass, right? That's the amount of protons and neutrons together is atomic weight or atomic mass. If we just count the number of protons, that's the atomic number. Excuse me. Remember, atomic number is how we organize this lovely periodic table. Atomic number, and do you remember what else? Starts with a P. Periodicity, good, excellent. That regular repeating pattern, right, of properties. Because remember, most of these guys in group 1, they behave similarly. Same thing with group 2. Same thing with group 17, group 18, right? Similar properties in similar groups. Okay? When they bond, remember that they're sharing or they're taking and receiving electrons. If they share electrons, what kind of bond are we making? Covalent. If they're taking and giving, that's ionic, right? And that's completely based upon the number of valence electrons they have, right? If you've got one valence electron, remember, you want to get to that magic 8 number, right? So if you've only got one valence electron, what are you going to do? I'm going to give it away. So therefore, I lose a negative, so I become positive. I become a positive, what do we call a positively charged particle? An ion, right? An ion is a charged particle, right? If I have 7, and I get your question, I promise. If I have 7 valence electrons, I only need one more to be happy, right? So what am I going to do? I'm going to take. Thank you. I appreciate that. I must have tapped it as I moved. Are you with me? Hopefully you stuck through that little pause on the recording if you're listening to this now. Okay, let's keep going. They're showing you that quick view that, remember, that first level only holds 2 electrons. So therefore, hydrogen and helium are the only 2 that are happy with 2 on their outermost. Everything else wants 8. At least 8. You can have more. Remember, 2, 8, 18, 32. Those are our different levels that they'll hold 1 through 4. You don't have to know that, but being reminded of that. We already talked about ions. We talked about ionic bonds, right? Again, where we have a positive and a negative ion attracting, and that one's taken, one's given. Now they're an ionic compound. Here's a picture that shows you that, right? That this chlorine has 7, this sodium only has 1, so it steals that 1. And now this is a positive, this is a negative, they're bonded together, and you've got lovely sodium chloride, which is salt, like what you sprinkle on your vegetables, right? Good. Covalence is where they're sharing, right? Remember, we can have multiple covalent bonds. Many folks only just make single covalent bonds. We can have double covalent bonds. We can even have triple covalent bonds. And those often form from 2 elements that are the same type. Remember those lovely diatomic elements? Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. They form oftentimes these multiple bonds. Hydrogen just forming one nice happy bond. Oops, I thought they had more, but I guess they don't. So we'll go back. We're cool so far? Again, this is like super review pieces. And we're already through about 3 or 4 on your chapter objectives. We've already covered all those pieces already. Molecules is when we've got 2 or more atoms that do what? They come together, right? And when we have those, you can call them a compound. Molecules, usually we mean covalent bonds. We won't get that technical in this class here. But they always have a definite kind and amount of atoms, right? So here's our molecular formula for glucose, which is something we'll use a whole bunch. 6 carbons, 12 hydrogens, and 6 oxygens that we've put together, right, to make this compound. We can also use a structural formula where we actually make the bonds with these little lines. Old school, right? You guys are very comfortable with this, I hope. Chemical reaction. When we take and we react these things together to make new things. The stuff we start off with, the things that are actually doing the reactants, the reaction, we call reactants. What do we call the stuff that's being made? The products, right? So reactants and products, right? Can you name the 5 types of reactions? Yes, give me one. Synthesis, give me another one. Yes. Decomposition, those are opposites, right? Synthesis coming together, decomposition breaking apart. Give me another one. Double displacement or double replacement. Single replacement. Now your textbook here groups them together as exchange reactions. That's fine. They're just saying, hey, we split. You take this, I take that. We're happy. Okay? So synthesis, decomposition, single, double replacement, and the last one, combustion. Thankfully, in our bodies, we don't do much combustion. Really not at all. Thankfully. It'd be a problem if we did. Now, there are gases from our bodies you can combust, but that's another YouTube video. You can check that out on your own. They talk about these reversible reactions, right, that go back and forth. It's all familiar, right? All stuff we talked about in detail last year. And catalysts are not part of a reaction. They just help it, right? They speed it up. Does anybody know what we call catalysts in the body? I'll be impressed if you do. Well, I heard it. An enzyme. An enzyme is a biological catalyst. We've got oodles of these. We'll talk a whole bunch about those in the future. Rolling? You guys are with me still? All right, talking about acids and bases. Acids being something that releases hydrogen ions. Bases being something that will accept those hydrogen ions. This is how they define it in this book. Remember last year we did OHs, hydroxides. If they give off, very few of those in our body. Mostly we define bases as things that combine with those hydrogen ions. An electrolyte is something that will give off ions in water. Electrolyte in your world, what do you think of? Gatorades, right? And that's what they're saying. These have these metals, these potassiums and these sodiums that will give off those ions, and so that therefore you've got these things that will conduct electricity. That's really what in our chemistry world we mean by an electrolyte. But giving off ions in water, for biology we call that an electrolyte. We're good so far? And we talk about acids and bases in terms of pH. Now you remember our pH scale, right? What's the bottom number? 0. What's the top number? 14. Which side, and I'll ask you a question in a second. Which acids are on which side? Lower. And the bases are? The higher. And what's neutral? 7. Water, though this water is not neutral. But yes, can be. Going up. The definitions here. Sure, right, that acids release hydrogen ions and that bases accept hydrogen ions. They're using, if you remember from chemistry, the Bromstead-Lowry definition of these bases. There are other definitions, and same for acids, other definitions, but this is what in this class we're dealing with. Yep. Yep. The bases bond with those released hydrogen ions. Sorry? Yeah. Yep. All right, so we just talked about the scale. Here's it in visualization. I thought this was kind of cool because it put on here, this is on what page in your textbook? 48? Okay, thank you. That seemed like a high number, but maybe that's right. 48. I liked it because it had stuff that we eat. Right? I mean, these are things that we take into our body on a fairly consistent basis. Garlic juice, apple juice, tomato juice, cabbages, corn, those are all acidic. Even cow's milk is slightly acidic. It's 6.6 on that pH scale. Okay? On the basic side, we don't have as many basic stuff. Our human blood is actually a little bit basic. 7.4 is our average. Sodium bicarbonate, does anybody remember what that is? What is it? Baking soda. That's sodium bicarbonate, right, in your cookies. You've got that. It's a base. Milk of magnesia. You have a ton of stomach ache, right? You take some Pepto-Bismol kind of thing. That's a form of milk of magnesia to help settle your stomach. I hope nobody is drinking household ammonia. I would not recommend it. It's a nice way to kill yourself. It's a cleaner, like a cleaner, ammonia.
Why would you drink that?
I don't know, because you're foolish. Are we good, my friends? Reminding you about pHs here. I will go back here. I'm going to mention this because we did not talk a ton about this last year, about buffers. So buffers are something that resist chemical change. So when acids are poured in, the base part of a buffer breaks it down and neutralizes it. If an acid comes in, it takes that acid and neutralizes that. Does this make sense? Its whole goal is to keep the pH from changing. In your textbook, let's see, where does it talk about the blood pH in your textbook? So go to page 48 in your textbook, and I hear your question. I'll come right to it. Okay? On page 48. Let's go here. On page 48, what is the range of pH that your blood can be in? What does it say? There's a little yellow box. What's our pH range? 7.35. Whew. So a pH of 7.35 to 7.45. This is the pH range of blood. When you go to the hospital, you're being admitted to the hospital. One of the things that doctors will do is they will do a blood pH on you. They'll run this whole CBC, Chem 7. You've heard them use all these phrases in the medical shows you watch. But one of the things they measure is the blood pH. Now take back a look at this list here. You drink some apple juice, and suddenly you are taking a pH of 3 and putting it into your system. Right? If I were just to have a thing of water here that was at a nice 7 point, we'll keep it, let's say we made it at 7.4, right in the middle of that range for your blood, and I dumped apple juice in it, are you comfortable the pH would go down quickly? Right? Because you just dumped in a bunch of acid into this, and that's what you're doing when you drink. Oh, I'm dumping acid into my stomach. Tasty. Right? My wife hates apple juice, but we'll ignore that for now. Okay? So apple cider is much better. So how does your body keep this pH from shifting all over the place? What if instead of apple juice, you ate a whole bunch of cookies? Oh, now we're talking. Lots of good baking soda in it, right? And the pH of your blood now goes up, right? These buffers are what resist that process. They're a combination of an acid and a base together, a weak acid and a weak base, if you think back to chemistry. And what they do is, as an acid comes in, the base part of that buffer neutralizes it. If a base comes in, then the acid part of the buffer neutralizes it. And it's these reversible reactions that it can go either way. So it can go from an acid to neutralize the base, or it can go from the base to neutralize the acid. Yes, ma'am? Well, in your blood, we're talking mostly about carbonic acid and a carbonate ion. Between the two of them, that's kind of the buffer system. We'll talk much more detail about these. But that's just a general term. We actually have a lab that we're going to do next week about buffers, just so you can see how it keeps us from these big swings of pH. And I have to admit, they say that our range is 7.35 to 7.45. If you're down 7.35, like that's a big deal. Like, you are sick. If you're up at 7.45, that's sick. I mean, you would not be healthy. They really want you to stay right about that 7.4 range, which again is amazing. With all the stuff we eat, it's amazing that our blood stays that little change. Yes, ma'am? Oh, no, not necessarily at all. Again, your body is designed, we can eat almost anything. You know what I mean? Our body can take a lot of things that you're like, really? That's food? And use it. So that's all right. Again, that's how the system was designed.
What about forgiving for donating blood?
So they will certainly check. She asked about donating blood. They'll certainly check to make sure there's no harmful problems. You kind of go through a screening process to make sure, hey, I'm actually okay to give blood. And if something pops up, they will take a look at that. It's not something they test. They test more the iron level in your blood, the hemoglobin level. That's when they prick. How many of you have actually given blood before? I'm just curious. Anybody in this room? Given blood? Nice. Nice. Yeah, they prick your finger and that's what they're looking at, the hemoglobin level. Are you with me, my friends? Okay. 10 minutes, good. Stand up for a minute. Stand up. Let's stretch a little bit. Whew. As we just zipped through 7 questions worth of pieces, and now we're starting to get into new stuff. But I want you to stretch. Give yourself a little bit of a. Whew. Should I do some acro gymnastic stuff? Do some. Because you guys will lead some stretches and stuff for us. Let you guys roll. You're good? You're awake? All right. Go ahead. Have a seat again. So now, my friends, now we dive into numbers 8 and 9 on your learning outcomes for chapter 2 in this chemistry of life. You can take all of these compounds that we've talked about. Remember, compounds meaning molecules, right? You've taken 2 or more atoms and put them together to make something new. We can divide them into 2 sections, organic and inorganic. Does anybody know what the difference is? Organics are better for you to eat, right? In the market, they're more expensive to buy the organic produce? No, that's not what we're talking about. Same word. An organic compound has what? I'll give you a hint. It's on the board.
Hydrogen and carbon.
Hydrogen and, really even more importantly, carbon. Shh, stay with me, guys. So an organic molecule has carbon as its base, as its like backbone. What's so fun about carbon? Like, why is carbon so special? How many valence electrons does carbon have? Some of you guys are over here. Carbon's right here, group 14. It's got 4 valence electrons, right? So what's our maximum? Like, what do we want? We want 8, right? So it's this perfect combination that it can sometimes give, it can sometimes take. It loves to make these nice covalent bonds. It forms these lovely chains. It does some very cool stuff, chemistry-wise. As a matter of fact, those of you who are going on and will do chemistry in college, there are whole classes simply called organic chemistry, where they'll go through all these different compounds and molecules in the body. Because you, friends, are mostly organic molecules. Okay? We are a lot of carbon. Yep. We are a carbon-based life form. Maybe you've heard that term before. That is the basis of all of our molecules is carbon. But we also have these inorganic compounds as well. So let's talk about a couple of them. The first one is water. That's how you all say it in Maryland, right? Water. Is this our water? I don't know, something like that. Water.
Hey, waiter.
There you go, some water. I used to always get the Sheehan's. The Sheehan's have good Maryland accents. You know, Blake, he's a water guy. So, are you comfortable that about 2/3 of you is water? Right? So that means, these things like this, right? And these things like this. I'm assuming this has water in it, right? These are good things. Yep. They are together. Yep, yep. I'm sorry? Yes, because of the oxygen that's in there. Yep. But why is water so important? We know it makes up so much of our body, but why is it such a big deal for us? Yes, ma'am. It helps out with the metabolic processes. Can anybody give me more? It's a solvent. Remind me what solvent means? It dissolves things, right? A solute is what is dissolved. Most of the reactions in our body need water to actually happen. Like you can pull them outside of water and they will happen, some of them, but it's very slow. So water is like the catalyst that makes things work much easier, right? It also transports things, talking about in and out of cells, through osmosis, around the body, through your lymph system or your circulatory system. It carries wastes. It absorbs heat. I will tell you truthfully, as a scientist, the water molecule is one of those things to me that says, hey, there has to be a God. Because this molecule is it's just two hydrogens and one oxygen. But this molecule does so much in our bodies, in our world. When astronomers are looking for places that aliens could live, what do they look for? Water. They look for water. If you've got a planet that can support liquid water, hey, that's a good bet that there could be something living there. Like, that's how important this is. Our next inorganic compound, oxygen. Why is oxygen important for us? We breathe, sure, but what do we do with that? Yes, sir. Man, that was almost like you read that right from the board. That's well done. Yes. Oh, yes, it releases energy from nutrients and is used to drive the metabolism. Absolutely. We're going to learn and be reminded again about that metabolic process, breaking down oxygen, breaking down glucose through that citric acid cycle and glucolysis and all that good stuff. Carbon dioxide. This is the waste product that's produced during the cellular respiration, during the metabolism processes in your cells. So it takes in takes in oxygen and gives off this carbon dioxide as a waste, which then we in the bloodstream roll it to the lungs and we breathe it out. Okay? Inorganic. Yes, it's right. It's a little funky because it has a carbon in it, right? But there's no hydrogen there. So usually organics have to have both the carbon and the hydrogen. There are, of course. But again, this is only carbon and oxygen, so it's still inorganic. Okay? Our last one is inorganic salts. And there's a whole list of them in your textbook. I think there's even a chart, right, that talks about some of the different pieces. Yeah, they're on page 50. All these inorganic salts. You do not have to know all of them, okay? What I simply want you to know is what is the role that they play, right? Again, at the study guide, know just in general, what is the function of these inorganic salts. We use them in our metabolic processes. In order for us to actually be able to break down our food and create energy from that, remind me, what form does energy take in our body? Do you remember? Not heat. Okay, energy is given off as heat. I like that. But the whole processes in our body is trying to create what in order for us to use that as energy? A little molecule. Not proteins. We take glucose and we break it down in order to make this that all of our cells use for energy. It's a 3-letter word. Not fat. ATP. Right? Good job. Adenosine triphosphate. ATP. We break everything down to make ATPs. And again, you'll learn this whole process. And these inorganic salts play a role in that. Whew. Good stuff. What I'm encouraging you, thank you, let me finish, is that we've gotten through all the way through number 8, right? And don't pack, please. Let me just finish, please. We'll spend some time with number 9. I do want to make sure you spend some time this weekend, certainly going through 1 through 8. You should be comfortable getting through those numbers 1 through 8 this weekend. We'll spend some more time on number 9. Might that test that I'd scheduled for Wednesday, might it pop back to Thursday? It might. But I want you to keep your mind focused on this weekend 1 through 8. Adios.